Okay, this is a differential geometry practice final exam. So let's begin. Here's number one. Let gamma of t equal a cosine t sine of t, a sine of t, bt, where a be greater than 0. So this is mostly computation, remembering all the formulas you have to apply and where. For letter A, compute the unit tangent vector. So this is going to be a helix. We take the first derivative, we get a negative a sine of t, a cosine of t, b. We calculate its norm. When we do that, we're going to get the square root of a squared plus b squared. So now to get the unit tangent vector, that's going to be equivalent to the gamma prime of t over the norm of that gamma prime of t. And that's just going to come out to that negative a sine t, a cosine t, b over square root of a squared plus b squared. Letter B, we want to find the curvature. So what we do, we already have the tangent vector. We want to find the derivative of the tangent vector here. So t prime here of t, negative a sine of t, a cosine of t, b over square root of a squared plus b squared. So our curvature here is, we have the norm t prime of t over y prime over gamma prime of t. Just substituting in here, this is what we're going to get. So we're going to wind up with a over square root of a squared plus b squared over square root of a squared plus b squared equals a over a squared plus b squared. So just in general, I'm going to omit some of the steps with computation just because for get you through this video more quickly, and I apologize if I misspeak because I'm going to try to talk fast during this. So for letter C, find the torsion. So here is the formula we employ for the torsion. Find the second and third derivatives of gamma. We get that. Then we take the cross product of gamma prime and gamma double prime, and we get this ab sine t minus ab cosine t a squared. Squared norm we have here. This is its squared norm. Okay, the squared norm, that denominator. And then we need to get the dot product of that cross product of y prime and y double prime dotted with y triple prime, third derivative of, and I shouldn't say y, it's gamma technically. So ab sine t times a sine t plus negative ab cosine t times negative a cosine t. That simplifies to a squared b. So substituting that in and simplifying, we get b over a squared plus b squared. So this is primarily all computational stuff. And for letter D, determine all values of a and b for which the curve has constant speed equal to 1. Okay, so let's see what we have here. So constant speed equal to 1. Set this norm of gamma prime of t equal to 1, and that's square root of a squared plus b squared equals 1, and consequently a squared plus b squared equals 1. Okay, that takes care of number 1. Hopefully I didn't miscommunicate anything or miswrite anything. All right, now we can move along to the second one. Okay, number 2. Okay, let's see if this holds up. Let me just get this more in focus. Okay, so, sorry about that. Consider the surface x of uv equals u cosine v, u sine v, natural log of u is greater than 0. So first we want to compute the coefficients e, f, g of the first fundamental form. So E, F, and G here, we want to get the partial differentials x sub u, x sub v. Here's what we get for the partial derivatives. Compute here. E equals x sub u dot x sub u. We're going to get cosine squared plus sine squared plus 1 over u squared. That's 1 plus 1 over u squared. We get our f, which is x sub u dotted with x sub v. That is 0. And our g is just going to be x sub v dotted with x sub v. That's u squared. So we wind up with our coefficients e, f, and g, respectively. We have for e, 1 plus 1 over u squared. F is 0. G is u squared. So we can move along to compute the area element in part B. Compute the area element dA. So dA is going to be, it's going to be the square root of EG minus f squared du dv. We substitute what we have in for EG. Okay, that clears out to square root of u squared plus 1, and our dA is square root of u squared plus 1 du dv. Just substituting and performing the computation. And letter C, find the angle between the coordinates u equals constant and v equals constant. So here, angle between coordinate curves. Coordinate curves are orthogonal if f equals 0. And in this situation, since f equals 0, the coordinate curves meet at right angles. Okay, so at the coordinate curves there. And letter D, determine whether the parametrization is conformal. So conformal requires this. F equals 0 and E equals G. In this situation, we have E equals 1 plus 1 over U squared, and G would equal U squared. Okay. Now, generally, these are unequal, the E and G, from what you can see. So the parametrization is not conformal. So that takes care of number 2. Okay, so now we get to the more interesting problems. Okay, so number 3, let's see if this holds up. Yeah, we're good. Okay, so number 3, let x of uv equal f of u cosine v, f of u sine v, g of u, where right there f of u is greater than 0. So we could compute the first fundamental form. So right here we're dealing with geodesics on a surface of revolution. So for first fundamental form, we take the partial derivative here, x of u, we get f prime cosine v, f prime sine v, g prime. Then x sub v equals negative f sine v, f cosine v, 0. So our E is going to be f prime squared plus g prime squared. We have f is 0 and g equals f squared. So in this situation, getting this fundamental form, we have this ds squared equals f prime squared plus g prime squared du squared plus f of u squared dv squared. And that's all for letter A. Okay, letter B, right here, using the Euler-Lagrange equations for arc length, show that along any geodesic, f of u squared dv ds equals c for some constant. Okay, so here we have part B. Arc length Lagrangian is L equals 1/2, this situation, times the quantity E, u prime squared plus g v prime squared. Okay, now here's what we can think about. Since L does not depend explicitly on v, Euler-Lagrange gives conserved momentum. Okay, so dl d partial there of dl d v prime, that's a constant. However, the dl, the partial dv prime, equals gv prime, and that is equal to f of u squared dv ds. So this f of u squared dv ds, that equals constant c. Okay, or equals C. Now, we're continuing with part B. Continuing. So part B down here continued, and we're going to go on to the next page, just so we have this down. For the geodesics parameterized by arc length S, use the energy Lagrangian. So the energy Lagrangian we're going to need is L equals 1/2 quantity E U prime squared plus 2 F U prime V prime plus G V prime squared. So we're going to need that for the next page, the next part of the problem. So let's see if this holds up here. Okay. Since F equals 0, we have that right here. L equals 1/2 times the quantity into parentheses F prime squared plus G prime squared times U prime squared plus F of U squared V prime squared. Okay, so that's what we're dealing with. Now, here's the nice thing. L does not explicitly depend on V. Okay? Now, therefore, we could say is V, about V is it's a cyclic coordinate. So, Euler-Lagrange gives a conserved quantity. So, let's just observe what we have here. So, dds of dl, partial d v prime, that equals 0. And the dl d v prime, that equals f of u squared v prime. And from there, so we could say d ds of f of u squared v prime, that also equals 0. And f of u squared v prime, that equals c. Right? And since v prime is dv ds, it's confirmed right there that f of u squared dv ds, that is equal to c. So that'll take care of letter B. Now letter C, we want a geometric interpretation of this. Okay, so we're right here, geometric interpretation. This is Clairaut's relation. So we could let psi be the angle between the geodesic and a meridian, a curve with a constant v. And we could demonstrate that right here, f of u sine of psi equals c. So going over here, sorry that I wrote this small. The interpretation, what we could say is f of u is the distance from the axis of revolution. And also, as the geodesic moves farther from the axis, the angle adjusts so that this quantity remains constant. And we could wrap that up with this portion. We could say this behaves like conservation of angular momentum in mechanics. All right. Now, in part D, we could apply this to a cylinder. So for a cylinder of radius r, f of u equals capital R and g of u equals u. And then Clairaut's relation becomes r squared dv ds equals c. R is constant, dv ds equals a constant. Metric is ds squared equals du squared plus r squared. Dr squared there. So the geodesics satisfy the linear equations we have here. The u of s equals as plus b, and the v of s equals cs plus d. And we could state that geometrically these are vertical lines, horizontal circles, and helices. So if the cylinder is unwrapped into a plane, what's going to happen to these? These are going to all become straight lines. Okay. So that's A, B, C, and D. That takes care of number 3. Again, I'm going through this rather quickly because you could pause the video. You could check the answers. Hopefully I didn't write anything down and make any mistake. Hopefully. Should be okay for the most overall. Hopefully. Well, I think the overall gist of it is all right. So, number 4. Let the surface patch be x of uv parentheses u v u squared minus v squared. So part A, we want to compute the coefficients of the first and second fundamental forms. So here we take those partials, x sub u, x sub v. From there, it's computation. With this part, we compute our E, F, and G. And respectively, for E, we get 1 plus 4u squared. F, we get negative 4uv. And G, we get 1 plus 4v squared. Okay, so we have a normal vector. And then we take the cross product here, x of u crossed with x of v. And we get the following, negative 2u, 2v, 1. And taking the magnitude of that, we get the square root of 1 plus 4u squared plus 4v squared. Okay? So, building on that, we could get the unit normal vector. So some more computation. Unit normal vector is going to be negative 2u, 2v, 1. The cross of x sub u and x sub v over the magnitude. So there is our unit normal vector. So after we get the unit normal vector, well, now we need to get our second derivatives. And partials. X sub uu, x uv, x vv. And we wind up with 0, 0, 2, 0, 0, 0, 0, 0, negative 2, respectively. So for the second fundamental form, okay, what we have here, we want to find E, F, and G, okay? So lowercase now, E, F, and G. So we had the first fundamental form, now we want the second. So E is going to be, lowercase e is x sub uu dotted with n. And when we do that, take the computation, it's 2 over square root 1 plus 4u squared plus 4v squared. And then our f, that's equal to, lowercase f is x sub uv dotted with our unit normal vector, that's 0. And our g is x sub vv dotted with the normal vector, unit normal, that's negative 2 over square root 1 plus 4u squared plus 4v squared. So E and G are very similar. So from here, we just write these respectively of what E, F, and G are. And that takes care of letter A. Okay, and now letter B, we want the Gaussian curvature. So this is going to turn out to be that K is EG, lowercase eg minus lowercase f squared over capital EG minus f squared. So this is a lot of computation just to reduce time. If we substitute the values and we break it down, we get K of uv. After we substitute, break this down, this is negative 4 over the quantity 1 plus 4u squared plus 4v squared squared. So that takes care of letter B, the Gaussian curvature. Okay, now letter C, we want to determine all points where the curvature vanishes. Okay, so this isn't that bad. Conceptual problem from stuff probably in textbook and notes. Okay, so determine where the curvature vanishes. Well, the numerator for the curvature, if you look back to part B, is negative 4, which is a constant. Okay? It is never 0. So your curvature of uv cannot equal 0 everywhere. So everywhere can't equal 0. So what we could say for letter C is there are no parabolic points. Okay? And now for letter D, we want to classify the origin. Well, take a look here at uv, 0, 0, k of 0, 0. Well, what do we get? We get a negative 4. Okay? And let's think about what that means. We get a negative amount that's less than 0. And in this situation, a negative Gaussian curvature, what does that imply? It means that the point is hyperbolic. So that point at the origin, 0, 0, 0, is a hyperbolic point. Okay, so that takes care of number 4. Okay, let's move along. Number 5, let's see if this holds up or not. Whoops. See, let's get a new batch. Okay, so let's get a new one on here. We'll put the 5 down. Let's see if this holds. Sorry about that. Just getting in focus. Okay. Consider that unit sphere. Okay. And we have gamma of t equals cosine t sine t 0. Let that be the equator. Show that gamma is a geodesic. So let's take a look at letter A. So the covariant derivatives in parallel transport, this is what we're dealing with here. So on the unit sphere, I'm just going to walk through here, letter A, your gamma of t equals cosine t sine t 0. This is the equator. So we're going to get the first and second derivatives of this. We get them here and here. And what we see here is that the second derivative of gamma is equal to negative gamma. So what we can conclude is, however, this being that the gamma of t is the outward unit normal vector to the sphere, all right? Acceleration as a result is entirely normal to the surface. And a curve is geodesic if and only if tangential acceleration, it goes away, it has to vanish. Okay, so what we could say here is we could conclude that right there that gamma is a geodesic. Okay, here for part B, we want to let v of t equal a negative sine of t cosine of t 0, compute the covariant derivative. So we want to compute this covariant derivative. Okay, and let's see what we get. We have that v of t. V prime of t would be negative cosine t, negative sine t 0. And we know that v prime of t equals negative gamma of t. All right, think about why that is. And the vector, we could say, is normal to the sphere. The covariant derivative is the tangential component of the ordinary derivative. And since v prime of t has no tangential component, we could say that this winds up as 0. So the covariant derivative is 0. Okay. Letter C, determine whether v is parallel along gamma. So a vector field is parallel along a curve if and only if its covariant derivative vanishes. Well, think about what happened here. Since the covariant derivative is 0, we could say that the v is parallel along gamma. And for part D, give a non-zero tangent vector field along gamma that is parallel. So, letter D, any non-zero constant multiple of v remains parallel. And an example in this situation, we could say w of t equals 2 times negative sine t cosine t 0. Okay, that's related to that first derivative function there. Okay, so that's A, B, C, D for number 5. Let's see, moving along to number 6. Let's see if it stays. Sorry about that. You know what? Let's take this off. And let's put this one on. Number 6 is up at bat. Okay, so let's see. So let w equal y dx z dy plus x dz. Okay, so that's what we have here. And we're going to have wedge notation in this. All right, so compute dw. All right, so we're dealing with differentials here, right? We're dealing with these differentials. Compute dw. So we're going to have wedge notation here. So d of f dx, df wedge dx. D of y dx is dy wedge dz, wedge product of. D of z dy, that's dz wedge dy, and d x dz of x dz, dx wedge dz. Okay, so let's see what we have here. So we say dw, if we substitute here, dw equals d wedge dx plus dz wedge dy plus dx wedge dz. Furthermore, up here, dy wedge dx, that's negative dx wedge dy, and dz wedge dy, that's negative dy wedge dz. And we could substitute into that dy, and we get the following here. Dy equals negative dx wedge dy minus dy wedge dz plus dx wedge dz. Okay, so we could say now, done with letter A. Letter B, let S be the upper hemisphere. X squared plus y squared plus z squared equals 1, where z is greater than or equal to 0, oriented upward, and we want to compute this integral. Okay? So here's what we could do here for B. So we have vector field. The vector field corresponding to W is F equals YZX. Then the cross product, okay, here, the del crossed with F is negative 1, negative 1, negative 1. And by Stokes' theorem, we could say this integral along the dw surface equals that cross product dotted with NDS. So this is Stokes' theorem, calculus 3, vector calculus, shows up again in differential geometry, shows up in physics a lot. So on the upper hemisphere, symmetry implies that this integral here, NDS, that equals 0, 0, pi. So the point negative 1, negative 1, negative 1, dotted with 0, 0, pi, that's negative pi. So this integral is negative pi. All right. And now we want to compute the line integral of this ds y of w directly for number 6. Okay, and let me just get this ready. So, yep, that's computing the line integral. Okay. So here we have the boundary of the hemisphere, that ds. Okay, that's going to be cosine t, s sine of t 0, from 0 to less of 0 to 2 pi. Take the partials, dx equals negative sine t, dy is cosine t dt, and dz equals 0. Substitute into w. Okay, so now dx, dy, dz. Technically, I'm sorry, these are the differentials, technically, right? These are differentials. W equals y dx plus z dy plus x dz. So, since z equals 0 and dz equals 0, w equals sine of t times negative sine of t dt. So that gives you negative sine squared t. And if we go ahead and we integrate this, 0 to 2 pi negative sine squared dt, what we could do is we could use 0 to 2 pi sine squared of t dt, and if we integrate that, we wind up with pi, okay? So it's just going to be the opposite value of that, in this situation, negative pi, okay? And for part D, if we want to verify Stokes' theorem, we just take the information we got from previous steps. So this integral dw, that equals negative pi from previous steps. And this integral here also equals negative pi. And if this negative pi equals negative pi, these two quantities come out equal. Stokes' theorem is technically verified. So that's letter D. Okay. Let's see if this holds up. Moving along to number 7. Let me just get this out of the way then. Okay, number 7. Okay, we're good? Yep. Let, okay, we have that R in the G, R2, be the plane equipped with the metric G equals e to the 2 y times the quantity dx squared plus dy squared. Okay, letter A. show that the metric is conformal to the Euclidean metric. All right, so let's do part A. So given this metric, g equals e to the 2y, quantity dx squared plus dy squared on R2, we could say a metric is conformal to the Euclidean metric if it has the form g equals lambda xy dx squared plus dy squared for some positive function lambda. Okay, so here, say g equals e to the 2y times the quantity dx squared plus dy squared. Thus, the conformal vector is lambda xy equals e to the 2y. That is greater than 0. So, therefore, we could state that g is conformal to the Euclidean metric. So that's part A. Moving on to part B. Compute the lengths of these two curves. Okay, gamma sub 1, gamma sub 2. So here's the formula we're going to need. The length formula is L of gamma equals, from A to B, square root of g of this y dot dt. So curve 1, all right? We want to differentiate. We get y dot sub 1, and that's at 1, 0, okay? So make sure we're using this formula for this component of these two sections of the problems. Let's see if this holds up. Okay, so, all right. So, since right here, y equals 0, e to the 2y equals 1, okay? And so, for g of this y sub 1, this y dot, substitute, we get 1 times the quantity 1 squared plus 0 squared, we get 1. So we're just going to wind up with L of y of, I shouldn't say y. Why am I saying y? It's gamma, right? It's gamma. I don't draw the best gamma, so I confuse myself visually there. Sorry about that. So if I said y, I meant gamma. My apologies. So L of gamma sub 1 equals the integral from 0 to 1 square root of 1 dt, and that's just going to be 1. So for curve 1, we get L of gamma sub 1 is 1. For curve 2, here's what we have. Same principle, similar operations, except here, after substituting everything here, L of y sub 2, we have the integral from 0 to 1 square root of e to the 2t, but that simplifies to just 0 to 1 e to the t dt. Integrating that, we just get e minus 1 for our L of y sub 2. So L of y sub 2 is e minus 1. Now for part C, the maps for this are t sub a xy equals now x plus a comma y. All right? Think about why that would be. Now an isometry preserves the metric. And here the metric depends only on y. We have a horizontal translation changes only x. So therefore, the conformal factor remains unchanged. So this e to the 2y, that maps to e to the 2y. And dx squared plus dy squared is preserved under translation. So we could say, thus, that t sub a is an isometry. Now for part D, okay, vertical. So this is horizontal, now vertical. So part D, S of B of xy equals x, now comma y plus b. So under this transformation, e to the 2y, this now becomes e to the 2 times the quantity y plus b, which becomes e to the 2b 2y. Okay, so from here, let's see what we can do. This isometric becomes e to the 2b g. And unless b equals 0, this is not the same metric. So vertical translations don't preserve lengths. So in this situation, S of b is not in isometry unless b equals 0. So that has to be the case in that situation. And now let's go along to number 8. Number 8. Okay, so let's see what we have here for number 8. Let me just get this in focus. Okay, so number 8. Okay, so let M, being R3, be a regular surface with unit normal field N. Part A, show that if N is constant on M, then M lies in a plane. So I'm going to go through this quickly just so you have it. But this would be definitely one of the more challenging ones. Think it through. That's an interesting problem, though. So letter A, again, show that if N is a constant on M, then M lies in a plane. So letter A, suppose N of P equals N naught for every point P in M, where N naught is a fixed unit vector. The tangent plane at each point consists of vectors orthogonal to N naught. Thus, every tangent plane is the same plane. Okay? So we have this notation here. And this means the surface never changes direction. Now, equivalently, the differential of the Gauss map, that's going to go away. It vanishes. So dn equals 0. And since all tangent planes coincide, the surface must lie in an affine plane, and I forgot to put orthogonal to, in an affine plane orthogonal to N naught. Okay, and that being the case, we could say, so M is contained in a plane. So that is letter A. Letter B, suppose every geodesic on M is a straight line. In R3, show that M is contained in a plane. Okay, so here's B. Geodesic on a surface satisfies the following. So its tangential acceleration is 0, and its acceleration is purely normal to the surface. Okay. However, if the geodesic is also a straight line in R3, then gamma double prime of t equals 0. So its normal curve is 0. If every geodesic is a straight line, then normal curvature vanishes in every tangent direction. Therefore, the second fundamental form is identically 0. Okay, so right here. And also the shape operator vanishes. S equals 0. So by part A, the surface lies in a plane. Therefore, M is planar. Okay, so that is letter B. And the last portion we have here, give an example of a surface for which some but not all geodesics are straight lines, and that is going to be a cylinder. Okay, so for part C, let's see if this holds up. So, a standard example is a cylinder. Okay, on a cylinder, vertical generator lines are straight lines in R3, and these are geodesics. However, helices are also geodesics, but helices are not straight lines. Therefore, some geodesics are straight, while others are not. So, a cylinder is such an example. And that's it for this. Hope this helps as a study tool for getting ready for a differential geometry exam. It's just practice. And have a great day. Thank you.